Mind-body problem is the problem of why the physical basis of a conscious experience, like the experience of red, is the physical basis of that experience, as opposed to a different experience, like the experience of green, or no experience at all. And this is a problem that predates Descartes, but Descartes really put it in the modern form. And there are a number of different responses to this. The two main ones are dualism, the idea that the brain and mind are separate existences that have only a very distant relation to each other. And physicalism, the view that the mind is the brain.
So today, as I said, we're only going to set the stage for what's going to come next throughout our semester. And this will simply be an introduction. We'll go over some historical landmarks that are important and relevant for the story, the narrative stream, the story of how we got to have this field that we call cognitive neuroscience, right, and what it means. The main relevant aspect is related to the mind-body problem, right? I mean, no wonder people have always asked, how do we get to feel what we feel? How do we get to see what we see and experience what we experience as human beings? What is it about our bodies physically that enables us to do all those things? So essentially, how can a physical substance, in this case the brain, can give rise to everything that makes us human? Our sensations, our thoughts, our emotions, so our mind. Right? So this is the mind-body problem. What is it that connects the brain to the mind? How is it that the brain, which is a physical element, you can touch it, you can see it, how is it that it enables our mind, which comprises all these processes that we cannot directly observe? And so there were different proponents throughout history of different ways or different approaches, conceptual approaches to how this might be resolved, how this mind-body problem might be resolved. So on the one hand, René Descartes came up with dualism. He said, well, the mind and the brain are two different things. They are made up of different kinds of substance, so we might as well just talk about them separately. A bit later on, Baruch Spinoza came up and said, well, the mind and brain are not entirely distinct. We might think of them as two levels of description of the same thing, right? We get a bit closer to what we understand today as forming essentially the basic philosophy of cognitive neuroscience, right? And this was termed dual aspect theory, right? So we have two aspects of the same thing. On the one hand, the mind, on the other hand, the brain, but they are not distinct. They are simply two different levels of description. Now we have contemporary philosophers like Paul and Patricia Churchland, who are some of the promoters of the approach we call reductionism. And you will see that reductionism is a valid, concrete scientific approach. However, it has its limitations and its criticisms. And for example, when we touch on, maybe towards the end of the lecture, when we discuss computational psychiatry and translational neuroscience, or translational psychiatry, we will see that reductionism comes short a little bit. But anyway, their approach to reductionism pretty much states that whatever we perceive as mind, as being part of mind, will be essentially, eventually, with the right tools and scientific advances and technological advances, be replaced by brain-based constructs. So in their opinion and others' opinion, others who promote reductionism as the best approach to solving the mind-body problem, they say we are actually just a little bit short of achieving a translation, right, between the mind and the brain, and substituting or being able to express cognitive processes exclusively referring to brain-based processes. Okay, this may be a bit extreme. In any case, there are a few books that you might find interesting if you are so inclined to dive deeper into this debate. So, for example, there's this nice book by Patricia Churchland called Brainwise, right? And I'm not sure, but I think this year you'll also study neurophilosophy. Well, if you do, I hope you do. It's a very interesting field that will hopefully foster critical thinking. And so an excerpt from this book by Patricia Churchland essentially states, she says, however brains work, much of what they do involves representing, right? And we will discuss representations as well throughout this course. So for example, we are able to represent our brain's body, the features of the world, and some events in the brain itself. And she says, performing computational operations on those representations serves to extract relevant information, make decisions, remember, and move appropriately. So a concrete example, for example, might be mental rotation, right? That would be one process, for example, where you can think of and imagine how performing those computational operations, right? Because you would just imagine, in a sense, rotating certain objects, right? That enables you to function in certain situations, to make decisions, and to move appropriately in your environment. And then she goes on by saying that brains represent and compute are working assumptions in much of cognitive neuroscience. So again, she is right. That we have to make assumptions when we develop our cognitive models that we then try and test in practice. And we see whether these assumptions hold or not. And this is part of the falsifiability of science. And I hope, again, that you will have a course on neurophilosophy, and hopefully falsifiability will be one of the topics that you will be discussed. So she says, I emphasize that these are indeed assumptions, however, not firmly established truths. And this is true for pretty much everything in neuroscience, in cognitive neuroscience at least. And especially when we study living humans, oftentimes we do not have access to studying the brain directly. And so we rely on models, on assumptions, and on indirect signals that we can record from the brain. And that's how it works in cognitive neuroscience. So we make it work. All right. But the important thing to remember is that we most often do not have a ground truth of brain processes. We make assumptions. We test those assumptions, we see if the results match up to those assumptions or not, then we move on. And finally, Patricia Churchland says, as science continues to progress, the assumptions may be amplified, revised, or even falsified, okay, which is what I mentioned before, in favor of better hypotheses, as yet didn't conceived, right? So if our results in one experiment do not match up to what we had hypothesized, maybe that opens the gate towards a different hypothesis, a different assumption, a better assumption, maybe one that's closest to the ground truth of how the brain works. Here's another great book if you want to dive deeper into the mind-body problem and how we navigate this field of cognitive neuroscience when we want to test out assumptions about the brain. So in the Computational Brain by Patricia Churchland and Terence Sejnowski, she says, if we are to understand how the brain sees, learns, and is aware, we must understand the architecture of the brain itself. Here you kind of see where this reductionist approach leads to, right? This is essentially a statement that fits with the reductionist approach, right? So in order to understand the mind, we must understand the brain, the physical construction of the brain. She goes on by saying the brain's computational style and the principles governing its function are not manifest to a causal inspection, right? As I said, we cannot test things directly on the brain. And causality is a delicate topic, a very important one nevertheless, but with cognitive neuroscience and especially with indirect methods that we mostly use when we test living humans, right? Having access to causal inferences is very hard, if not impossible. And so very few of the things that we know from most cognitive neuroscience studies do not necessarily enable causal inferences, right? They mostly present us with correlations, as in neural correlates of various cognitive processes, but those are not causal statements. So I will reinforce this idea throughout anyway. So that's important to understand. And she goes on by saying, nor can they be just inferred from behavior, detailed though the behavior descriptions may be, for the behavior is compatible with a huge number of very different computational hypotheses, only one of which may be true of the brain. And this is another issue that is predominantly acute when we discuss MRI, fMRI, right? So what she says, and this is true, if you look at an observable behavior, that behavior may have a various number of underlying neural mechanisms and neural processes behind it, right? So just by observing a behavior, we cannot state with any confidence what the brain process behind it might be. And this is the reason behind a lot of research that I also do on differential diagnosis, for example, between, in my case, because this is my personal interest, between autism and schizophrenia, for example, because clinically, observationally, certain features look similar, and just by looking at behaviors and phenotypic manifestations, we would call them, right? You cannot always make an accurate diagnosis, or you cannot always come up with a useful prediction, long-term prediction for that particular person. And so that is why we need additional tools. Okay. And so she also goes on to say, moreover, trying to guess the governing principles by drawing on existing engineering ideas has resulted in surprisingly little progress in understanding the brain. So here she alludes to the appeal, let's put it that way. The appeal that, for example, in our day and age, machine learning offers us, right? We look at it as if it might help us unravel certain mysteries that are otherwise inaccessible, but the promise is not yet easy to fulfill. Okay, let's put it that way. And so at the time when this book was published in 1996, this was before the machine learning boom. However, there were other computational approaches that seemed promising at the time, and this is one of the reasons why I wanted to also include, at least at the end of the semester, something related to computational psychiatry and computational neuroscience, right? That's just another way of looking at the brain and trying to model brain processes. And some of those computational implementations, like dynamic causal modeling, I'll talk to you about that when the time comes, tries to tap, for example, into causal mechanisms, okay? But again, these are computational models. And since we do not have necessarily access to the ground truth, we don't really know for sure whether things are expressed in a certain way at the brain level, we have to take them, with a grain of salt. But this is just to emphasize the wealth of approaches that are focused into trying to solve this mind-body problem. Okay, and so finally she concludes by saying, and the unavoidable conclusion is that there is no substitute for conjuring the ideas in the context of observations about real nervous systems, from the properties of neurons and the way neurons are interconnected. Okay, so still our best chance is to look directly at the brain, but in absence of that, we do our best. Okay, and throughout the semester that's the point. We'll learn about different methods. I'll especially emphasize their limitations and their advantages. And so when you become a researcher, if you decide to go into research, essentially you will choose the method according to your research question, not vice versa. Okay. So knowing what each method brings to the table is extremely important.
Now, some people react, like my colleague David Chalmers, for example, by espousing dualism. I'm a physicalist. I think that you should think of the mind and brain as the same thing, but you have to answer the question of why it is that our different concepts of the mind and different concepts of the brain pick out the same things.
So where are we today? Have we made any progress on the mind-body problem?
One of the, I think, advances that has been made on the philosophy end is to realize that this isn't that different from other cases in the history of science where people have had incredible puzzles. My colleague Tom Nagel put it in a way that I think has been very important, which is that you can have two different concepts, a mental concept and a physical concept, and not have any idea how they can pick out the same thing. One example, but it's a very simple one, is the fact that water is H2O. Now, the concept of water that we have from ordinary life is not one that it's immediately obvious how it goes together with some kind of chemical concept. But we have found out that when you take water apart, you get these chemicals. And so we know that water is just a bunch of H2O molecules.
Well, let's start with water in the wild, so to speak, and in large quantities, because in our...
And I think our problem with the mind-body problem is a little bit like that, in that we have these mental concepts and the physical concepts, and we don't see how they get together.
One of the things you're especially well known for is the distinction between access and phenomenal consciousness. What exactly do we need to know about phenomenal and access consciousness?
Phenomenal consciousness is experience. It's what its likeness of perceiving, the redness of red or the smell of a rose. Access consciousness is a matter of using that perceptual or other information in reasoning and control of action. Sometimes you are aware of a sound, like say when the refrigerator goes off, but also aware that you have been hearing it in the past. Now, if there was a time in the past when you were hearing that hum, but it didn't come to your notice, it was something that might have been something that was phenomenally conscious, but not something that you were in a position to think about. So that's an example of phenomenal consciousness, possibly without access consciousness.
Let's go a little deeper into this. What does it mean to be conscious in the phenomenal sense of something that you can't mentally access?
Well, the idea would be that there is some perceptual or imagistic quality to it, that what its likeness, but something that is you've prevented yourself from being able to think about. But it might come out in your dreams or your slips or in other ways, and we might be able to have evidence that the brain processes that are going on are characteristic of perceptual experience, but are prevented from getting to your centers of reasoning and control of action by some powerful repressive mechanisms.
Our colleague at NYU, David Chalmers, has called phenomenal consciousness the hard problem of consciousness. Why is this such a hard problem?
So the idea of the hard problem is to distinguish between the mind-body problem, as I explained it, how it is that the neural basis of an experience is the neural basis of that experience. To distinguish that from what he calls the easy problems, which are issues to do with the function of consciousness, where we can get a handle on how consciousness does certain things that it does. And he's really just the idea of the hard problem is to pinpoint that mind-body problem, that we do not have an explanation. Now, he goes on to conclude that the physicalist idea of the mind is wrong. Whereas I go the other way. I think we've got a big problem to solve, but I'm more focused on the progress we've made and the hope that that progress will continue.
Ned, a controversial topic is animal consciousness. What do you have to say about this? Well,
certainly in the sense of phenomenal consciousness, what it's like to experience red, I think that our visual systems are very similar to those of many higher mammals, especially, and I think very likely we have very similar perceptual experiences, especially visual experiences, as they have. So I differ from some people, though, in that I don't think the frontal lobes are very important. The frontal lobes is where the basis of thought and where we differ enormously from animals. But I think you can have phenomenal consciousness without much in the way of frontal lobe involvement. And so I think we share that kind of perceptual consciousness with at least many mammals.
So what about non-perceptual consciousness?
Well, like emotions?
Yes, emotions, for example.
I think those have a much larger cognitive component. So I think maybe we're less likely to share those.
And so you attributed phenomenal consciousness to primates. But what about other mammals?
Well, I think the further you go down the phylogenetic tree, the more doubtful it gets. Once you get to the point of fish, which have very primitive brain and nervous system, I think it becomes doubtful whether they have consciousness. Maybe there's not even any answer to the question whether they have consciousness or not.
What would Tom Nagel have to say about that, since he has this idea of what is it like to be a bat? Well, it's like being a bat. So isn't being a worm or slug like being a worm or a slug?
I think Tom thinks, as do I, that for some animals, or some creatures anyway, there's just nothing it's like to be them. There's something it's like to be a bat. They're not that different from us, but there's nothing it's like to be a slug.
One of your many contributions has been to help transform philosophy from a field of ideas to a field that's also interested in testable ideas. Tell us about this.
Well, I think what's happened is that many philosophers, especially philosophers of mind, have realized that there are all these interesting things happening in the sciences of the mind, and that those interesting results that have come up can be of use in thinking about traditional philosophical problems. So here's an example. One of the a standard philosophical problem is the problem of the speckled hen. How it can be that you seem to see all the speckles on a hen, but somehow you can't count them and you're not sure how many there are, even when there aren't very many of them. Now, in some cases, it's because you can't remember which ones you've counted, but even aside from that, there does seem to be a problem of being able to somehow focus on individual things, even though you seem to see them all. Well, I think a good, at least partial solution to this comes from work on attention. It turns out that the grain of attention, the smallest area that you can attend to, is larger than the grain of vision, the smallest area of space that you can see. So it's the mismatch between these different grains that explains at least one aspect of the traditional speckled hen problem.
So how does this insight from the speckled hen problem help us understand the bigger problem, the mind-body problem?
So you remember I said, from the physicalist point of view, the solution to the mind-body problem, or at least the framework for a solution, is to understand how your mental concepts and your physical concepts can pick out the same thing. Part of doing that is making finer grained distinctions both on the mental side and the physical side. So that's why it's important to distinguish on the mental side, for example, between phenomenal consciousness and access consciousness, but also why it's important to get a finer-grained understanding of the concepts of attention and consciousness and these different kinds of consciousness. So it's only by making conceptual progress and putting that together with scientific progress that we'll be able to put those things together and solve the mind-body problem.
This is a huge topic, not entirely resolved. I will touch on it a little bit when we discuss TMS, because Ned Block does make this distinction in his interview between having an experience and being aware that you're having that experience, right? So with respect to awareness, at least, I don't know if some would call it that consciousness, but at least with respect to awareness in the visual domain, there are some very nice TMS experiments that test essentially the pathways that enable a person to be aware of a visual stimulus. But yeah, just to preface that, we'll touch on that a little bit, but we won't dedicate a huge topic, a huge part of the course just to consciousness. That's definitely beyond my expertise as well, but we will discuss it in the context of visual perception and visual awareness. Okay, so where did things start, right? Let's go back to the roots, because before achieving, right, this methodological unity that is cognitive neuroscience, things needed to evolve on their own, first in parallel, and then they came together finally in what we today call cognitive neuroscience. So first of all, we had to have a scientific psychology established, right? And we distinguish this from common sense psychology. Okay, so scientific psychology is the systematic study following scientific method, and I hope you will learn about the scientific method if you have the neurophilosophy course. This is essential. Everything we do in cognitive neuroscience is based on the scientific method. So not just thinking about things, but also coming up with ways in which we can test hypothesis, right? So this would form the basic of scientific psychology, and this started with a few very important names, one of them being Hermann von Helmholtz, and so in the beginning, he studied physiology with Johannes Müller, and Johannes Müller was an experimenter and a naturalist. And at that time, he had written this book, Handbook of Human Physiology, right, which attracted a lot of interest because it was a systematic effort of putting together everything that might be known, that was known at that time about human physiology. And so this caught the interest of Helmholtz, who then went on to study medicine with Johannes Müller. And then Helmholtz branched out, and you can read the whole story on the Stanford Encyclopedia of Philosophy that I linked here. And so then he branched out, he came up with his own theory, and he proposes the so-called sign theory. And what the sign theory essentially says is that sensations, right, that we feel are reflections of the stimuli, the objective stimuli in the environment, but they are not a direct copy, so they are not the same thing, right? And this is something that, if you remember from last semester, I think when we discussed sensation, somatic sensation, touch, right? And I showed you those psychophysical experiments where you could determine someone's sensitivity, right, on the surface of the skin on different parts of their body. So psychophysics pretty much studies the relation between subjective sensation, right, and the objective quantifiable physical properties of stimuli. And so Helmholtz suggested this early on, right? He hinted at this, that what we feel for example, through the form of touch or taste or smell, is reflective of the chemical properties or the physical properties of objective stimuli around us, but they are not direct copies, right? And you can see why, because the same objective stimulus may be perceived differently by different people. And so Müller explains this correspondence between sensation and object by means of an innate configuration of senses, right? So this was Müller's hypothesis, but Helmholtz argues against it, and he says we construct that correspondence by means of a series of learned unconscious inferences. This adds on top of that, and in a sense goes further than Müller and says, yeah, okay, we may have, right? And we saw last semester that we are born with a certain pre-wired capacity for perceiving certain stimuli, but that is by no means sufficient, right? And so we need to be exposed to certain experiences in order for us to be able to fully construct the experience that is elicited by our interaction with the stimuli in our environment. Very interesting. I encourage you to go ahead and read the entire article. Now, another very prominent name that I think you will perhaps meet with in other courses that you have, perhaps cognitive science, I hope, is Wilhelm Wundt. Okay, and he is considered the father of experimental psychology, and he laid the grounds for this in his 1902 book, The Basis of Physiological Psychology. Okay, and again, last semester I mentioned, but I will just say it again here. This wonderful website, Classics in the History of Psychology, offers a wealth of materials, very understandable translations or commentaries of many of these classical writings in psychology. And here you can see, for example, an introduction to the main ideas in Wilhelm Wundt's book. Going on to William James, again, I expect that you will learn about him again. He wrote another prominent book laying the foundations of scientific psychology in his book Principles of Psychology. He states that he wrote this book following what he called the psychological method of introspection, okay, which to him at least means the looking into our own minds and reporting what we there discover. Okay, so again, these were the early days. The concept of the scientific method or experimentation was still in the beginning, and people weren't sure how to access the mind other than by introspection. And this was at the time the tool that they had. However, that's not to say that they didn't believe that the brain supported the mind, right? They didn't believe that in the dualism approach. And this is illustrated, for example, by the fact that William James in his book also included chapters on the functions of the brain, right? So, or also a chapter called On Some General Conditions of Brain Activity. Okay, and so he argues for the reductive and materialist thesis that habit is at bottom a physical principle. Okay, so he is more of a reductionist in the sense, or a dualist, saying so two descriptions of the same thing, except at that time, right, the tools were simply not there, and so he used introspection. And again, I would encourage you to check out this entry on the website Classics in the History of Psychology, where you can read a lovely description, overview, introduction to William James's book. And so this was how scientific psychology started to take shape as a field of its own. But the experimental methods were not quite there yet, and so enter behaviorism, right? Well, behaviorism was born precisely from that dissatisfaction that at the time people wanted to find out more about the mind and wanted to study the mind, but they didn't know how, right? And so behaviorists behaviorism was born from this dissatisfaction with the lack of systematic progress in the study of mental processes, right? And so experimental methods like what we saw before, introspection, right, and subjective judgments appeared imprecise, because they were. And so that's how a group of psychologists, especially in North America, started emphasizing highly controlled experiments, right? And they focused then on measuring as precisely as they could the relationship between experimental stimuli in a controlled experimental setting and measurable, observable behavior, right? And that's how this approach came to be known as behaviorism. Their main focus was to achieve the highest possible objectivity with respect to interrogating how the mind works. Okay? And so they wanted to reject anything that could have to do with subjectivity. And so they said they rejected subjective work on mental functions as being outside the domain of proper scientific inquiry. Okay, they simply didn't have other tools, but they wanted to be as objective as possible. And so they focused on this relationship between stimulus and behavior. This is what we can observe, this is what we can manipulate, therefore this is what we'll focus on, said behaviorists. Okay, and so we have two very, very prominent names. I trust that you will for sure learn about them more also in developmental psychology. So the father of behaviorism is considered to be John Watson. And he is most famous or infamous if you look at it through the lens of modern day science and ethics, but this was a different time and era. So he is most famous for Little Albert experiment. Have you heard of this experiment? Has anyone heard of it?
Yes.
Okay, so you know about it. Can you explain a bit?
Yeah. We studied in the psychology course in the first semester, and he made the little Albert, the child, be scared of the rabbit, I think. It was a rabbit or I don't know.
Yes, by producing a very loud sound, right? So pairing a very loud sound with a stimulus that otherwise produced no effect on its own before this conditioning, right? And why I wanted to mention this, so you already know, that's great, thumbs up, thank you. You will see this kind of pairing of stimuli with loud sounds or maybe electric shocks, not harmful but unpleasant, okay, in modern day experiments as well. For example, looking at anxiety, right? And then measuring that, for example, in that type of setting, using skin conductance, right? And that's why I wanted to include peripheral physiological methods. So, for example, you can have people, let's say, some that have high trait anxiety, some that have low trait anxiety, and you can compare them in an experimental setting to see how quickly, let's say, they become conditioned to associate an otherwise neutral stimulus with an unpleasant experience, right? One that can elicit anxiety, such as also in the case of Little Albert, a very loud, sudden noise. Okay, I've included here a link to a YouTube video that also shows some footage from the actual Little Albert experiment. You can watch that in your own time. And then another name that is very, very prominent in behaviorism is Skinner. And he developed this concept of operant conditioning. Okay, so stimulus, response, and consequence. And so he essentially worked, for example, with pigeons, and the pigeons learned to perform certain movements, such as, for example, turn around. When they were shown the word turn, of course the pigeons couldn't read, but they could see that there's a specific pattern, and they were expected to turn around when they saw that specific pattern that we could read as turn, and then they received a reward. And so this is how they were able to learn. Okay, so again, you have this pairing between a stimulus and an observable behavior. A stimulus that you can manipulate experimentally, an observable behavior that you can then quantify. And again, there's a lovely YouTube video that shows some archival footage with the pigeons in action. But maybe you already know this as well from the first semester from other courses. Okay, so enter cognitive science. Right? We talked about behaviorism, so only looking at stimulus and response, only looking at objective physical stimuli that one can manipulate and quantifiable behaviors, and then linking the two together. Now, cognitive science wasn't happy with this kind of black box approach that the behaviorists adopted. Because the behaviorists didn't ask questions, as you saw, as to what happened in the brain in between the stimulus and the response. Since we do not have methods to investigate that, well, that's what they said at that time, we don't have methods to investigate that, we'll just disregard it. Well, cognitive science came in exactly to build on that kind of gap. Okay, and this was bolstered, right? This new desire to explore actually this black box that interposes between stimulus and response, because in the mid-20th century, we saw technological advancement in the form of computational science and information theory, right? So computers started becoming a thing. And this gave people hope that, oh, finally, this might offer a model, a synthetic model for how the mind works. And so now we find this mind as computer metaphor. Okay, and here a name is very important for you to know, Claude Shannon, right? He's the father of information theory. And so information theory in mathematics refers to the quantification, the storage, and communication of information. Pretty much what we look at the brain when we explore it as well, right? We want to see how and where the brain quantifies certain stimuli, right? We know the visual cortex now quantifies and stores visual information and communicates visual information to other brain areas, right? So people then used this template of information theory to try and study the brain more systematically. And a very important concept, which is central to information theory, is entropy. Okay, loosely speaking, entropy reflects a state of disorder or randomness or uncertainty. The reason I want to highlight it here is because we can also talk about brain entropy, and certain analysis that we can perform, for example, on fMRI signal, help us quantify brain entropy. And this is based on the Shannon entropy, okay? Which, as stated here on the right side, is a measure from information theory, as we already said, that quantifies the uncertainty of a system. And so the logic behind it is that a system that is capable of producing multiple states has a greater entropy, right? There's more randomness, there's more uncertainty with respect to which state is the brain in at that particular time, let's say. As information in information theory is conceived as the reduction of that uncertainty, right? If we have information about something, we have more certainty about that particular something. And so Shannon entropy, from this perspective, is also a measure of the information capacity of a system, right? And I can also, when the time comes, show you some example from my own work where I look at how long information is stored in different brain areas. And so from all this, it follows that a brain with a larger repertoire of neural states has greater entropy, right? And so has greater information capacity as well compared to a brain with a smaller repertoire of states. This is pretty abstract, but I just want to add it here so that you don't disregard these concepts as being just part of history and nothing more, because modern analyses build on these concepts. And so this, at a glance, is essentially the difference that I was stating between behaviorism and cognitivism. So essentially the behaviorists conceptualize this black box in between a stimulus and response, and we'll just ignore it, right? Because we don't have access to it, we don't have the necessary tools. That's not to say, as I highlighted here, that they denied the existence of internal mental states. They did not. Of course, they understood that the brain does the thing that has to happen for a stimulus to elicit a response. They just didn't know how to approach it, and so they wanted to focus on what they could objectively quantify and manipulate. But cognitivism, of course, came up and said, well, now we have information theory, we have these computational models, so we can try and use this template to model, right, to try and infer what might be happening in that black box. And this is essentially the difference between them. And because now we already talk about a cognitive science, it might be a good time to explain what cognition is, right? So when we say cognition, we essentially refer to this collection of mental processes, like thinking, perceiving, imagining, speaking, acting, planning, everything that we'll discuss essentially the semester after we are done with the methods. And so this laid the foundations for something that we know today as the cognitive revolution, right? This is what is an intellectual movement, just like behaviorism was an intellectual movement at its in its time. So the cognitive revolution, again, was an intellectual movement, began in the 1950s. That turned the focus on this black box that is the mind and the brain, right? And this is how cognitive science was eventually born. And the prominent example of the cognitive revolution and kind of the first models of how the brain does certain things was David Marr. David Marr formulated a hypothesis as to what sort of computations might be happening in the visual system. He approached other topics as well, but I think he's most well known for his 3 levels of inquiry with respect to visual processing. And this is a wonderful book if you have a chance to read it. And so he posited that there are 3 levels of inquiry at which we can that we can use to build upon in order to infer how visual processing happens. And so on the one hand, first of all, he said, well, first we have a computational level. Meaning, if we investigate this computational level, we essentially try to find out what computations does the central nervous system perform and why. Okay, so what neural processes are there that enable us to perform certain functions, such as vision. Then there's the algorithmic level. And so here we go into details and say, okay, now we kind of know what computations there might be. How are these linked with each other, right? How are these stacked? How are they working together to form an algorithm, right, with distinct steps that eventually enable, let's say, vision? And then finally, implementation. Okay, and at this level, we ask questions such as, what are the physiological mechanisms that enable these algorithms to be implemented so as to produce, for example, vision? Okay, so you see, he does not disregard the biological aspect of vision, right? He does reference computational and algorithmic approaches as part of this kind of inquiry, but ultimately we also want to know how all these computations and algorithms are implemented physically, biologically. Now I've included these here. I won't necessarily stop to watch them with you, but I highly encourage you to watch them in your own time. Nancy Canwisher, I hope you remember from last semester as well. This is part of the series from where we extracted that video that we watched last semester as well, when we discussed the visual cortex in V1, and she was explaining the concept of retinotopy. Well, here she discusses Mars levels of analysis, and the way she explains things is so much nicer than I could ever do it. So I encourage you to watch her lecture. And then also Steven Pinker, maybe you've heard about him before. Well, here in this very short video, he explains the context in which the cognitive revolution took shape. Now, on the one hand, until now we saw how we got to have scientific psychology as a field. Then we looked at how from there we came up with behavioral measures and behaviorism. Then that led to cognitive science. Well, we're still not at the point of cognitive neuroscience, so something else had to take shape in parallel until the two fields merge. And this is obviously neuroscience, and this is not new information. We already talked about these things last semester, but I would like to refresh your memory nevertheless. So as we stated in the beginning, this is the reason why we will also discuss lesion studies. The first knowledge of brain function came from observing, right, brain injury. These were not experiments, these were just observations. And we have very, very early evidence that people paid attention and they were able to document some sort of connection between brain damage in certain brain areas and behavioral impairment. And so here I gave you also last semester the example of the Edwin Smith surgical papyrus. Then closer to our time, right, we have this skull that was received by Ephraim George Squire in Peru that showed a sign of trepanation, right? And this essentially hints towards intentional brain surgery, right? So first people observed, well, if there's a brain lesion here, then that happens to the person. Well, subsequently, they wanted to try and make controlled interventions on the brain in order to alleviate certain symptoms. And so this is one of the first examples. And Paul Broca, who eventually popularized the knowledge that trepanation existed early on, we'll discuss about him again when we discuss language. He made some of the first observations between brain lesions in what we now know as Broca's area and something that now we know as Broca's aphasia, right, which is a language impairment arising from certain from brain lesions in Broca's area. All that when we discuss language. And so this field, the scientific field that deals with the investigating how certain brain lesions lead to certain behavioral impairments, is called cognitive neuropsychology. Okay, so we're we're one step closer to cognitive neuroscience, but not quite there yet. So this is still the field of cognitive neuropsychology, which essentially it covers the study of brain lesions, right, and their impact on human functioning. Now, again, you will remember that throughout history, people had some interesting debates, right? Some thought, like Hippocrates, that the brain is important for the mind, that the brain enables us to function as humans. Well, Aristotle thought the heart was the seat of human mind. I will not go into details here. You remember probably this from last semester. Now, this is important again, and I wanted to emphasize how important Galen was throughout the history, because he was the first one that we know of, at least, to have done experiments to specifically test how the brain influenced behavior. And of course, at that time, the experiments were not very sophisticated, but nevertheless, they can still be considered experiments, and it's admirable that he had that kind of insight. And again, this is information from last semester, but I wanted to again add it here. And another important step before we get to have what we now call cognitive neuroscience was finding out, right, how brain processes were enabled, how do brain areas communicate with each other, how neurons communicate with each other, and finding out that this can happen through electrical signals was a huge step. And I hope you remember this again from last semester, and we'll see that certain experimental methods like EEG essentially rely on measuring electrical activity of the brain. Okay, so this was an important step forward. And because of this, then people were able to stimulate electrically isolated parts of the brain and observe the effect on behavior. And prominent names for this were John Hewlings Jackson, who studied epilepsy, and then Fritsch and Hitzig, who studied this in dogs, right, experimentally. Finally, you remember the homunculus and Wilder-Penfield. So again, building on the knowledge that the brain functions via electrical signals, he was able to map the somatosensory cortex using this kind of systematic stimulation of the brain. And finally, this is again essential, the neuron doctrine, right? Realizing that individual neurons are not just one big mush, one big mass of brain, but they are independent units that can be very specialized and that we can study individually. Now, phrenology again was a huge step forward. We may look back at it now with condescension, but for that time this was a huge step forward, because essentially it brought together the idea of functional specialization, right? So directly stating that certain brain areas likely specialize to support certain cognitive functions. Okay, and the logic behind it, as Franz Josef Gall said, was as the skull takes its shape from the brain, that's what he thought, right? The surface of the skull can be read as an accurate index for psychological aptitudes and tendencies. That was his thought behind this connection between the shape of the skull and inferring how some people may be more adept at performing certain functions, certain cognitive functions compared to others, right? Because he posited, well, if your skull is bulgier in some area, then that means the brain is bigger in that area, and therefore that area of the brain if he thought supported a certain function, then that would be more accentuated in that individual. That was kind of the logic behind it. We know it's not like that now, but making this step, connecting the individual brain areas to potential functions, individual functions, was an important step in the thinking process that gets us closer to cognitive neuroscience. And finally, here we are, right? Cognitive neuroscience. This is now the intersection, right, between cognitive science and neuroscience. So on the one hand, we have the brain. On the other hand, we have the mind. We want to study them together because we understand now that the brain supports the mind, right? Cognitive processes, and we would like to know how that happens. Okay, and this is the field of cognitive neuroscience. And again, I highlighted here something I mentioned before, that most of what we are able to find in cognitive neuroscience are neural correlates. Okay, these are not causal mechanisms. So there are merely correlations between what we can observe using the tools of cognitive neuroscience at the brain level and what we can observe and measure at the behavioral level. So this is something to be very mindful of. Okay, so for example, when you read a paper, you can take a look at how far they might go with the interpretation of the results, and you can then assess whether it's reasonable to conclude certain things based on what the method can give you, what the results can show. Okay, so be aware of this distinction between neurocorrelates and causal mechanisms. They're not the same thing, and it's rare that we can say anything about causal mechanisms using indirect measures. One thing to remember, though, is that the methods that we'll discuss are complementary, right? They can be used together. They can be used also separately, but then we can look at how results converge, and this would be, and this means that we can look at the results coming from different methods or multi-model settings from a convergence point of view. Right, so we can measure something. For example, one of my projects deals with the excitation inhibition ratio. However, because I work mainly with fMRI, that is a very indirect measure. I don't have access to measure directly, right, concentrations of neurotransmitters, so I use a computational approach to estimate that. On the other hand, there's magnetic resonance spectroscopy that is likewise a non-invasive, but that looks directly, or, well, I couldn't say directly because still it's non-invasive, but is more finely tuned to assess concentrations of neurotransmitters, right? So here we have, for example, a case of convergence, right? Knowing, for example, from magnetic resonance spectroscopy literature that the excitation inhibition ratio is altered in certain clinical groups, in certain brain areas, I can see then if I can find convergent results using the computational approach based on fMRI. That would be a concrete example. Okay, so don't disregard a method because, as I said, you choose your method according to your research question, and multimodal approaches are not only valid but also encouraged in modern cognitive neuroscience. And this is because different methods have different limitations, and by combining multiple methods, then we might be able to compensate, right, for certain limitations. And so that's just something to keep in mind. And there are different criteria behind behind choosing a certain method. On the one hand, yes, it's the research question, but what exactly is it about the research question that might lead us towards one method or the other? Well, for example, we need an understanding of what the temporal or spatial resolution of a method is, right? If we are interested, for example, more in where in the brain something happens, then we might go for a method that has a higher spatial resolution, like fMRI, compared to EEG. If we are interested in how fast a cognitive process unravels, then we might go for a method that has a better temporal resolution, even though it may not have a very great spatial resolution like EEG. Alternatively, we can combine the two. We can record EEG signal from a person that can also be then put into a scanner, right, an MRI scanner. So there are things to consider then. Now, another criterion might have to do with whether your research question would be better suited going for an invasive or a non-invasive method. As I said, with living humans, non-invasive methods are pretty much the only group of methods that we have at our disposal, unless you work with clinical groups that have already, for medical reasons, implanted electrodes. Like such cases might be, as I said, with patients with epilepsy or with Parkinson's. And in that case, you can have more direct or invasive methods of recording. Another aspect, for example, is portability, right? For example, if you want to study sports, right? How the brain acts when people perform different motions, maybe they play a sport, then you would want them to be able to have a wearable device, right? That they can use out in the field when they play that sport. And so portability is also important because of that. And there are, for example, EEG EEG settings that one can walk around and perform activities with, right? Eye tracking is another example. If you have eye tracking systems based on glasses that people wear, that's another example of highly portable method. And so these are the trade-offs that you need to consider, right? And these are just some of them. Now, there's a variety of methods. I already mentioned this last semester. We'll talk about most of these and more. And finally, we will focus on cognitive neuroscience, but there are different branches of neuroscience that you might go into, and these are again synergistic, right? They don't exist in isolation. So, for example, translational and clinical neuroscience, right? We want it to be in communication with cognitive and behavioral neuroscience, because ultimately what we want to do is take results from the lab to the clinic, right? Have concrete implementations in some of the cases, unless it's fundamental research. At least the work that I do, I hope to take it to the clinic, right? So I am a cognitive neuroscientist, but I aim for reaching out towards a more translational approach. Okay? Computational neuroscience, as I said, is a tool that I use frequently as well, precisely because I work with indirect measures of brain activity. And so the hope is that some computational approaches allow for more precise inference, or maybe even causal inference, which otherwise would be impossible.